I'm seeing that the tornado looks really good at the top because you start to see a lot more rings toward the top that are like intersecting with each other. But towards the bottom, it's just like this ring doesn't even touch anything. So I think it'd be really cool if there were more rings toward the bottom to fill that dead space, and less rings at the top because we don't need them as much. When I is equal to 9, our final value also has to be equal to 9. And when I is equal to 0, our quadratic value also has to be equal to 0. But everywhere else, we can have a more interesting curve. So let's get both equations on here, right? This is y equals x, where x is I, and y is our output value. This is what we're currently using. This is doing nothing to I, basically. Y is equal to x squared is a cooler value. Let's say we scaled this down. So instead of I being 1, 2, 3, 4, 5, 6, 7, I is like 0.1, 0.2, 0.3, just for a second. So when I is equal to 0.1, the height that we get with this red line is also 0.1. But the height that we get with the blue line, the quadratic line, if I can actually get to 0.1, is 0.01, which means we're not going to increase as much. And we're going to increase more and more until we get to this 1-to-1 value. We need this graph to cross at x is equal to 9. So what we really need to do is widen the graph. Widen the graph. We're going to do square root. This is our number of bodies. So I'm just going to use a b for bodies. So when we have 10 bodies, like I showed, it's going to cross at 10. And remember, it's bodies minus 1. Now it's crossing at 9, which is what we've got. That's pretty much it. That's how we do this. So as long as our transform graph intersects at the beginning and at our final value to our linear base value, as long as those two intersections are met, we are still going to have the same height tornado. It's just the spacing between the different loops will be different. And what's cool about this is I can kind of change this square root to whatever I want to get kind of different shapes. So if I make this a, rather than just doing a straight square root, I can do b minus 1 to the power of 2, to the power of 1 over 2. So now I can make this 2 a variable. So I'm going to call this p for power. So when it's 1, it's just a straight line. Can't really do much with that. But at 2, this intersects there. If I make it a 3, oh, wait a minute. This intersects right at 3. Why haven't I made it 4? Seems my math is a little goofy. Oh, right, because this ends up canceling out if I do something like this. If I do something like this, then you have to distribute the p. Really, I could have just written it like this. X to the power of p divided by b minus 1. Ooh, is it just p minus 1? Sometimes I just guess and check math. I'm not even gonna lie. That's it. It was p minus 1. It was p minus 1 the whole time, guys. God, all of that was to say that if I want to make the slope more or less intense, then I can use a more general formula. In this case, x is I, b is the number of bodies, and p is whatever power I choose. So let's do like, let's add a power here. We'll start with 2. Oh, apparently power is an actual function. So I'm going to have an x width interpolator as well as this height interpolator. So we'll call this one the height interpolator. And this is going to be equal to power I comma p, so I raised to the p, divided by power b minus 1, or b is number of bodies, minus 1, raised to power minus 1. So everywhere I've got an I, I'm going to change with this height interpolator, which is going to dramatically increase the length of my lines, but that is a-okay. Oh no, hold on, I don't want, okay, I'm sorry. I don't want to use my new interpolator with current width. I still want that to be linear. I want to use it with my height though. Yeah, let's use something different for the current width. So I'm going to run this now to show what happens. Yeah, so notice how we have kind of a bowl shape. That's because we're still using a linear width for the individual ellipses, but we're not drawing them at equal intervals. Rather than going from 10 to 9 and then 9 to 8 and putting them equidistant from each other, 10 to 9 is super far down, and 9 to 8 are closer together. And that's literally what we're seeing right here. So we can't just get the width by interpolating that. What we have to do is we have to get the y value, which is here, and then we'll just use a function of y. So current width is equal to, we'll use the lerp function. So we're interpolating between the min height and the max height. But rather than getting our width from our I value, we're going to get the width from where we actually are in the y direction. So our amount is going to be center y. Oh, but remember, so this is a different value, right? So this is now going to be our ellipse offset y, and then we are subtracting that. Ellipse offset y. So let's look at why we just did that. This is the raw distance that we've traveled, but remember, this surf y gives us an offset for our actual position. So we don't want the literal position of the tornado to affect its width. We only want which position the ring is relative to the tornado itself to affect the width. I hope that made sense. But basically, as the tornado moved, if we just used our center y, as the tornado moved, it would change heights, which would make absolutely no sense. Now we have ellipse offset y, which is a value between 0 and our max height. So if we divide this by height, then we're going to get a value from 0 to 1. And we'll be interpolating from 0 to 1 our minimum height and our maximum height. Later on, we can replace this lerp function with a better formula that describes the tornado itself. But for now, lerp is fine because it's just linear. What did I do? Max height. Max height does not exist. Ah, there it is. I'm sorry. It's a value between min width and max width. My bad, guys. Anyway, yeah, so look at that. Now it's working. We have lots of stuff down below and fewer things toward the top. So now what I'm going to do is I'm going to go crazy. Let's add 100 bodies instead of 10. Well, 100 might be too many. Let's do like 25. Actually, what I can do is I can add some playability here. So if I go to, so now I can change the number of bodies and decide what looks the best. It might be worth it to go for like a power 3. And remember, so we have this weird thing in the graph when we use a power of 3 where it goes down past 0. But remember, we never go below 0 and we're never going above this value. 3 looks like this. Let's change our scroll wheel to change the power value. Yeah, so this is what happens as I'm increasing the values. And if I wanted to be able to control a lot of things and really mess with this in real time, I can set like buttons to change what I'm messing with. Okay, next up, we kind of want to do the exact same thing actually. Like, we're going to be reusing this. So now what I'd like to do is I'd like to create this kind of shape in the tornado, where it's actually like doing this, right? And then you get your tornado following that path. It's literally the same thing. The width increases slowly at first and then a lot towards the end. So we'll call this PH for power height. And now I can actually spell out power. So this will be power H. And let's do a power width. And we're going to replace this lerp function. This is the value that we're interpolating. I'm going to do width interpolator is equal to something eventually. But for now, it replaces this. Okay? So if I were to replace that with like that, if I were to do that, our width interpolator is linear. But that's not what we want right now. So our ellipse offset y divided by height is kind of like our I. And this is actually from 0 to 1. So this this even makes it easier than what we were doing before. It's going to be this power to the power of PW. That's the whole thing. Because this is exclusively less than 1. Or sorry, it's from 0 to 1. So it's inclusively less than 1, I guess. But anytime we're less than 1, when we square something, our value gets reduced. Which means our width will grow slowly at first and then quickly at the end. Check it out. Now that's what I call a freaking tornado. I think this is the last thing I'm going to do for the stream. This next thing I'm doing, which is going to be super cool. We're going to make it wiggle. We're gonna do some wiggling. Heck yeah. And the best way to make something wiggle is to put a sine wave through it. So finally, we're going to mess with this center X. It is no longer just going to be the center X. What we want to do is... So now we need a time value, because now everything is going to be time dependent. Time equals 0. At the end of our update, we do need to increment time. So we'll do time plus plus. And then what I do in draw is center X is going to be plus sine time, and then times some scale factor. So first I'm going to multiply time by pi, just so that it's... Later I'm going to want to bake this into a sprite, rather than having it run dynamically. So having it a multiple of pi is going to make it so that it's more easy for me to loop. If I don't multiply by pi, since pi is irrational, it will actually never repeat, which is not my favorite thing when it comes to having sprites that are less than an infinite subimages. Yeah. Infinite subimages sprites is... Infinite... Yeah. Sprites with infinite subimages are very difficult to work with. Your computer can't even load them. So now every time time increments, we go a full circle, which is a lot. Our tornado room runs at 30 frames per second. We can change it to 60, but I'm definitely not going to be... I don't think any sprite in the game runs at 60 FPS, so that doesn't even make sense. The actual animation, I mean, not movement. Movement is still 60 FPS. I don't want to get crucified by the gamers. But actual animations are not 60 FPS. So time increases 30 times per second. If I were to divide this by 30, it would take 1 full second to complete the sine wave. So it would go back and then forth and then back to center 1 time. Well, it's a sine wave actually. So it would start at the right, go all the way left, go all the way right in 1 full second. Cool, right? The only thing is it's only moving 1 pixel. Let's add another constant value here. Max movement. And we'll make that like 6. So now I can go back and forth 6 pixels, which is a total of 12. So there it is. It's going back and forth. Thing is, the whole tornado is moving together, and real tornadoes don't look anything like this. Well, real tornadoes don't really look anything like what we're about to make it look like. But fake tornadoes that I'm basing this off of look like what I'm about to show you. Problem is, this sine function doesn't take into account the height of the tornado, the height of the ellipse in the tornado. If we take that into an account, we take like the ellipse offset y and offset the value of the sine function by that, then different parts of the tornado will move at different times. It makes sense. Trust. If I say it makes sense, it makes sense. Unless you're also in the weeds and you do trigonometry nonsense because you're a game developer, this is probably like way too in the weeds. If I click 4, yeah, 4 is wave precession. So I'm going to increase that. 9, 10, 11, 12, 13. Oh, I have to increase it a lot more than I thought I would. 20. Yeah, like all the way up to 20 is crazy. Well, now I feel like I have to change some other values. Yeah, like all of a sudden I like the width a little bit bigger. And then... Oh, wow. Wait, having way more bodies now looks much better. Okay, wait. Now I'm just having fun. This is why nothing ever gets done, man. I get like halfway to something good and then I just play with it. So what you would imagine is this wouldn't all be rings. this would be like an actual sprite rather than the ellipses. And I think I might even do a little bit of that just to get a taste of it. Actually, there's one more thing we could do. I can then take center Y, and it's gonna be crazy. So we're using sine for X. We'll use cosine here. Let's hold on. If I use cosine, it's gonna be exactly the same. It's just at a different point. Same with the sine value. I just have to use the other one. This will make it so that no one's confused. Why are you using sine for X? Why are you using cosine for Y? Doesn't matter. It's all the same. So I'm gonna switch it to make it not confusing. Circular movement value. I know that's a really long name, but it's also a really long formula, so it's fine. You can always copy and paste your variable names. What you can't do is figure out what the heck your singular letter variables meant 2 weeks from now. So just give yourself long names. Also comment your code. I'm not going to comment my code because I don't have to, but you have to. Just kidding. Haha. Anyway. So then I started blasting. Right, so if I use center Y and add circular movement value, and also max movement, well, here. Max movement, remember, divided by 3 because that is our ratio that makes it look like projection is happening. It makes it look like we're actually looking at an angle. That should be all we need. So now this should move in like more of a circular pattern and might be really, really cool. Well, it'll move in like an elliptical pattern, but your brain will tell you it's circular. Oh my god. Guys, we cooked. That was it. That was the last piece of the puzzle for sure. That looks brilliant.